we will find a power series solution to this differential equation. So first, we write out the power series for y, and then we take the derivative and the second derivative. That's what we have. And then we will substitute into the equation the second derivative, n equal to 2, and then the rest, just go ahead and write it down. That's the second derivative, x plus 11, the first derivative, and then the function. That's supposed to be equal to 0. And then I will multiply x into the middle series and then 11 to the middle series. Just rewrite the rest of the problem. Now if we multiply x inside, we increase the power of x by 1, which is x to the first power. And then the 11, I will bring inside the summation. So we have 11 a to the n power n x to the n minus 1. Just multiply by 11. And the last series stay the same. In order to combine the series, we need to see where the series start at. The first series, when n equal to 2, so we have x to the 2 minus 2. So this start at x to the 0 power. The middle series, we start at x to the first power. The next series, we start at n equal to 1, x to the n minus 1, so x to the 0 power. The next one, we start at x to the 0 power. So everything except the second start at x. So in order to combine the series, all the series must start at the highest power. So all the series must start at x, so we can combine them. Because of that, we have to split some of the series, except for the middle, except for the second one. So when n equal to 2 on the first series, we have a2. I just keep forgetting the n here. Sorry. That is the second derivative. We should have n there. N equal to 2 though. So that's what we have. X to the 2 minus 2 will be x to the 0 power. That constant. We don't need it. Next, since we have n equal to 2, the series now can start from 3, go on to infinity. So n here, n minus 1, x to n minus 2. Right. The next series start x to the first power, so that's good. No need to change anything. A sub n x to the n. The third series start x to the 0 power, so we have to split 11 a sub n when n equal to 1. So we have 11 a sub 1 n equal to 1, x to the 1 minus 1 will be x to the 0 power, so that's constant. And when n equal to 1, that's what we have. So now the series can start from 2 to infinity. and we stay the same. And the final series, we have to split out a naught x to 0 power. So the series can start at n equal to 1 to infinity, an xn equal to 0. So all the series will start x to the first power. We can combine them. Right. Also, we now combine all the loose terms or isolated terms. We have 2a2 plus 11a1 plus a0, and now the summation. Actually, I need to write very compact because of this. We don't have a lot of space here. 2a2, 11a1, and a0. Now, the first summation. We're not going to write like that. What we actually need is make sure that we have the same power as well. Because all of the series, they start 3, 1, or 2. We need all of them consistently start the same number. So first, if we match this term to x to the k power, meaning that n minus 2 is equal to k. So n is equal to k plus 2. So for the first series, that is, we have n equal to k plus 2. K plus 2 equal to 3. K must be equal to 1. So we start at k equal to 1 to infinity. Remember, n is equal to k plus 2. So we have k plus 2 here. K plus 2. K plus 2 minus 1 is k plus 1. And the power will be x to the k power. The next summation, this should be easy because all we need to do is replace n to k. So we just say k equal to 1 to infinity, a to the k, x to the k. And then seems like we're missing something. Right. Sorry, I forgot the n here. There's an n here, so that should be n there. So the second series, we have a sub n and x to n minus 1. Sorry about that. So because of that, we do miss a k here. Sorry, just n, not n to the k minus 1. X to the k. Right, ak. This is n. Right. Once again, when we multiply x to it, we will have an n here, and that would be a sub n and x to the n. So this will be what we have. Right. And now we turn all the n into k, so we have x to the k power. Sorry, that should be what we just have. Right. And then the next, this we do start from x to the k power. So n minus 1 is k. So n is equal to k plus 1. And we have n equal to 2, so k plus 1 equal to 2. So k will go from 1 to infinity. We have 11 a of k plus 1, because that's what n is, k plus 1, and then k plus 1 x to the k. The last one is easy. We just replace n by k. And we have that. Now the first, on the isolated term, what we have here. Now on the series star at k equal to 1 and the power of x to the k power. So we can factor out k power, and all of them start from 1, k equal to 1. So we have ak plus 2, k plus 2, k plus 1 times x to the k factor out, and then ak times k plus 11 a to the k plus 1, k plus 1 plus a to the k, and x to the k is a common factor. Right. Now the right hand side is equal to 0. That makes all the coefficient on the left hand side equal to 0. So let's write down what we have. By the way, A1 and A0 has no restriction. So we have A0 equal to A of 0. A1 is equal to A1 because there's no restriction. Those coefficients are arbitrary. Right. From here, we can solve for A2. So A2 equal to A0 bring to the other side, we have negative 1/2 A0. And 11A1 move to the other side and then divide by 2. So that's what we have. By the way, this problem we need to write the solution up to x cubed, up to order 3, meaning up to x cubed, which means we need A3. So to find A3, we have to use the summation. We start k equal to 1, so let's start with k equal to 1. Now if we put 1 into the coefficient, we will have A3, so that's what we're going to have A3 later. K is 1, so we have 3 and 2. A is 1. A is 1 and A is 1. That coefficient must be equal to 0. Now all we need to do is just solve for A3. We have 6A3 here, plus 2A1, plus 22A2 equal to 0. So if we have A3, so A3 will be equal to negative 2A1 move to the other side, divide by 6, so we have 1 over 3A1 plus, actually 22A2 move to the other side is negative 22A2 divided by 6, so that's minus 11 over 3A2. We do know A2 is equal to negative 1/2 A0 minus 11/2 A1. 1/3 A1 minus 11 over 3 A2. Now I substitute negative 1/2 A0 minus 11 over 2 A1. Combine like terms, we should have actually there's no only A0 there, so it will be 11 over 6 A0. And then A1 we have negative 1/3 plus 21 over 6, and that is 119 over 6, positive 119 over 6. A1. Right, now we're going to write the solution. Y as a summation n equal to 0 to infinity A0x A1x, I'm sorry, A0 is a constant, A1x, A2x, and A3, A1x, A2x2, A3x3, and A4x4, and so on. Now we don't have anything about A0, so we have A0 plus A1x. A2 we can say is equal to negative 1/2 A0 minus 11/2 A1. So that is A2, and A2 multiplied by x2, right? And then A3 is 11 over 6 A0 plus 119 over 6 A1, and that is A3 must multiply by x3, and the series goes on. And then if we factor out A0 and A1, we should have A0, A0, 1, minus 1/2 A0 x squared. A0 factor out, so we just have x squared, and then 11 over 6 A0 factor out, and that x cubed. Of course, the series keep going with that. And then the another series with A1, we start from x plus, actually minus 11 over 2 A1 x squared, A1 factor out, so we just have that. And then plus 119 over 6 A1 factor out, so be x cubed, and the series goes on. And that's what we have. Let me zoom out and review what did we do for this problem. So pretty standard from the beginning. We will write y and own the derivative as a series, and from that we have own the series. Again, there are three important things when we combine the series. First, they have to start at the same power of x, and we change off that start at the power of x to the first power, and then we will split every term out, so that every series we start at x to the first power. And after that, we do need to do the transformation so that make sure everything will do raised to the power of x to the k. And with that, we combine the series. The right hand side is equal to 0. All the coefficient must be 0. And after that, we solve for all the coefficient. This problem asks us to find up to order 3, meaning we need up to A3. We have to solve inside the summation. And for the first one, for k equal to 1, we have A3. So when k equal to 1, we have A3. If we want A to the 4, A4, we need k equal to 2, and then we do the same recursion relation, and we can get 8, 4, and so on.